Today, we'll be investigating prokaryotic DNA replication.
First, the enzyme DNA helicase comes in and nips the DNA fragment by clipping the hydrogen bonds that hold together the two strands of DNA. It basically functions to unzip the DNA to make two single strands of DNA. This is the origin of replication, the point where replication will begin. When unwinding the DNA becomes supercoiled, but in order to reduce the torsional strain on the double-stranded DNA, an enzyme known as gyrase comes in and relieves this strain. In order to keep the two unzipped single strands of DNA from reannealing to one another, single-stranded binding proteins are attached to various locations on each strand. You can now see that I have added the labels of 5' and 3' to the ends of the two single strands of DNA. Recall that DNA strands are anti-parallel. Let's start by looking at the bottom strand of DNA. First, RNA primase will come in and lay down the complementary RNA primer. This primer is essential as it allows for complementary DNA nucleotides to be laid down by DNA polymerase III. RNA primers are made up of RNTPs, and the energy in the three phosphate groups of each nucleotide have large amounts of energy that allow for their synthesis. DNA polymerase III comes in and lays down the complementary DNA sequences while also removing the single-stranded binding proteins. Since DNA polymerase III can synthesize nucleotides only in the 5' to 3' direction, this strand can be synthesized continuously. This is what we call the leading strand. Next, DNA polymerase I comes in and removes the RNA primers and replaces it with DNA base pairs that are complementary to the parental strand, synthesizing them in the 5' to 3' direction. Notice that there is a missing link between where the DNA polymerase I just acted and where the DNA polymerase III had previously synthesized the complementary base pairs. The phosphodiester bond between these two DNA sequences of the leading strand are then linked by the enzyme ligase. Phosphodiester bonds are what link the backbone of a DNA nucleotide sequence together to make it continuous. Now let's look at the top strand. Notice how the directionality of this strand is opposite of the leading strand. The top strand is known as the lagging strand. Although the direction of replication is to the right, DNA polymerase III can only synthesize nucleotides in the 5' to 3' direction. In order to accommodate this difference, RNA primase comes in and lays down various RNA primer sequences in the 5' to 3' direction. Next, DNA polymerase III comes in and begins adding DNA nucleotides, starting at the 3' end of each RNA primer sequence. Once it gets to the start of a new RNA primer, it stops and skips to the 3' end of the next primer so that I can add more DNA base pairs in the 5' to 3' direction. Each of these segments of RNA primer and DNA base pairs are known as Okazaki fragments. Then, DNA polymerase I comes in and replaces RNA primer with complementary DNA base pairs in the 5' to 3' direction. The enzyme ligase can then come in and link the Okazaki fragments together by creating phosphodiester bonds between the base pairs of these DNA sequences. DNA polymerase I is a holoenzyme, meaning that it has more than one functional unit. It can use its exonuclease activity in either direction to replace RNA primers with DNA nucleotides. If DNA polymerase I did not have its 5' to 3' exonuclease abilities, RNA primer sequences could not be removed in the forward direction.